So, good morning all. Is it audible clearly? Is it audible? Okay, great. So, let us start. In this, actually, suppose if I give the task of analyzing a fluid flow, then can you think of a method how you can analyze, or what is the reference? How do you want to analyze a fluid flow, right? So, is there any method you can think of? I just given the task in the fluid flow. I am asking you to analyze it for a particular fluid particle. So what is the methodology you can adapt? Any idea? Okay, so here actually, so there are two persons. One is the Lagrangian and another is the Euler. So these are the two people actually, first time they have given a methodology. So these methodologies, the first one is the Lagrange's method. So what he suggested is, suppose if there is a fluid flow like this, and there is a fluid flow that is happening like this. Now, to analyze this fluid flow, take the fluid particle as the reference. Suppose if I take one fluid particle here, and this fluid particle is continuously moving from here to here like this. Now, take the fluid particle as the reference, and then try to identify the locations at different positions where it is getting traveled, right? And then try to verify the property of this fluid particle. Verify the changes of properties by taking fluid particle as the reference. So this is one methodology. So this was suggested by Lagrange. Suppose if I take one fluid particle, this may be having a different velocity here, and this may be having a different velocity here. And the same fluid particle may be having a different acceleration here, and at this point, it may be having a different acceleration. Now, you are identifying one fluid particle as a reference and trying to trace over the entire path how the properties of this fluid particle is getting changed. And this methodology was suggested by Lagrange, but this is a little bit complex methodology, but it will give more accurate analysis for us. And then the second method suggested by Euler. So what he suggested is, rather than taking the fluid particle as the reference, you take the space coordinates of the fluid flow as the reference. That means here actually think of a simple case like this. If the students are coming into the classroom, then identify each person and then try to trace the properties or his behavior over the entire path of the travel before coming to the classroom versus after he is coming to the classroom. Got it or not? So you are taking the person as the reference there to identify the property. But rather than that, the other methodology suggested by Euler is, so keep an observer at the gate and then try to identify. So the person you take as the reference who is observing all the students, and then get a report from him saying that who is behaving how. So this methodology is nothing but you are identifying one location and then he is trying to observe all the students whoever is crossing that point, and then he will be giving a report out of all the students. And that methodology was adapted by Euler in the sense, so in the entire fluid flow path, take the space coordinates. These are the coordinates. That is, if you take some coordinate system, this is 0, 0, 0, and then each location is identified as x1, y1, z1. Similarly, this point is x2, y2, z2. Like this actually, the locations are identified and these locations are taken as the reference. So, and then you are identifying the properties of all the fluid particles that are crossing this particular space coordinates. You are not taking the fluid particle as a reference here. Got it or not? This methodology is called Euler's method. Right? So this is an easy method because we can use the field concept here. And then this is a little complex. So that's why these methods for all practical purpose, so it was ignored and we will be using only this Euler's method. Whatever the stream concept yesterday I have explained, that was part of this Euler's analysis. Got it? So note down this Lagrange's method by taking one fluid particle as the reference, try to identify and trace the property of the fluid particle. For example, velocity, acceleration, mass. So all these things actually we are going to study. So these are the some of the properties that we are interested to study. So these properties, by taking one fluid particle as the reference, we are going to study. So that means, so the fluid particle, if you are planning to study, then you have to identify at least one location where it started, right? That was called as the initial position of the fluid particle. So let the initial position of the particle be A comma B comma C. So this is the initial position. Then what you are planning to study is at any instant of time which is started at this location, how the property of the fluid is getting changed. That means you are trying to identify. So R is equal to A comma B comma C comma T F of. So this is as if like the initial position plus a time variation you will be taking. So where F is the fluid property in general. Right? So this is how you are going to study in case of Lagrange's method. Got it? Note down this. Fine? Noted down? Okay. So in general, we call this as, so in our normal differential equation solutions, what we are studying, right? The way we are studying any particular physical problem statement. So that is the same method as if like it is the Lagrange's method. But Euler's method is a little bit new concept, right? Usually when we want to study any differential equation, what we are studying is, we take a differential equation and we will solve it, and then we will try to identify the initial condition, substitute the initial condition, and then try to identify the exact position or exact property at that particular time, right? So that is the standard method. So Lagrange's method is a standard method of analysis, but that is a little bit complex because many fluid particles are there, and all those things actually you need to be studying in a different manner. So that will be a little bit complex process. But Euler has given the other method, that is the field concept. Or this is also called as Euler's equation. So this one, what he suggested is, take the space coordinates of the fluid as the reference, and study the fluid property velocity, acceleration, mass, etc. All these are the fluid properties. Study the fluid properties by taking the space coordinates as the reference. Which are crossing that particular space coordinate. So this was suggested by Euler. So this methodology is called as Euler's method. Got it? So here, let the fluid property be F. Then this fluid property at the space coordinate of x, y, z at any instant of time t, right? At any instant of time. Here, these are variables. Earlier, these are constant. That is the only difference. Got it? So this is how actually it is going to be analyzed, where q is the velocity. For example, if you take a simple case, q is equal to ui plus vj plus wk. Now here, so here u is nothing but time rate of change, or q can be written as r comma t, f of r comma t, right? So R, this can be written as dou x by dou t into I plus dou y by dou t into j plus dou z by dou t into k. So this is how the velocity or for example a fluid property which we call as the velocity, that was expressed in this format. Here if you notice, all these things are the functions of the space coordinates and a time altogether. So this methodology, so here f of r comma t, where r is nothing but xi plus yj plus zk. So you are expressing this as a function of r comma t. That means the space coordinate and the time together. But here in the Lagrange's method, you are not expressing as a space coordinate. You are taking the initial position wherever it may be in the space, and then from there this property is getting changed with respect to time alone. Rest of the things are constant. Got it? Understood? Yeah. So this is the Euler's method. You can note it down. Then okay. So these are the concepts that are there. These are the basic concepts. So based on this, we'll solve some problems and then we'll go to the continuity equation. Note down one problem. The velocity vector q is given by q equal to xi minus yj. Determine the equation of the streamlines. Determine the equation of the streamlines. Can you solve this? I hope you have got a fair idea on the streamlines. I have derived the equation or the methodology yesterday. Equation of the streamlines is straightforward. So this can be written as q is equal to xi minus yj, right? And the equation of the streamlines will be so dx by u is equal to dy by v is equal to dz by w. So here u is equal to x and v is equal to minus y and w equal to 0. So you can ignore it. And then dx by u is x is equal to dy by minus y. So these two are equal. Or this is, if you integrate on either sides, this is log x is equal to minus 1 into log y plus log c, right? So this is log c by y is equal to log x or xy equal to c. So this is the equation of the streamline. Got it? Now what are the shape of these streamlines? So if you are asked to draw the streamlines, these streamlines is a rectangular hyperbola. Like this, right? Correct or not? depending upon the C value, these lines may come in first and third quadrant, or it may come on the second and fourth quadrant also, depending upon the C value. If C is positive, one section, and if the C is negative, then it will be the other. So all these things are the streamlines equation. Got it? So rectangular hyperbola. Understood? How we are finding out the streamlines? Yeah. Note down one more. The velocity q in a three-dimensional flow field the velocity q in a three-dimensional flow field for an incompressible fluid is given by q is equal to 2x into I minus yj minus zk. So that is the velocity. Determine the equation of the streamlines passing through the point now it should be fine. Okay. Solve this problem. This is exactly the similar manner what we have done in the previous problem, but the only thing is to know the arbitrary constants, the initial condition was given as the point. Okay, see this, q is given. Now the equation of the streamlines are dx by u is equal to dy by v is equal to dz by w. So this is the initial condition. Now you can take any two out of this. So here if you integrate, so take this dx by 2x is equal to dy by minus y. So integrate on either sides. This is 1 by 2 times of log x is equal to minus log y plus log c, or this is log c by y is equal to half log x or log x here 2. So x is equal to c square by y square, or xy square is equal to some arbitrary constant c. So this is one set of streamlines wherein the relation in between xy is given here, and then you can take these two again or these two, which will give one more relation. That is, if I take dy by minus y is equal to dz by minus z. So if you integrate on either sides, this is log y is equal to log x, so log z plus log c, or y is equal to cz. So y is equal to cz. So if you want the relation between x and z, then substitute the y value here. So then it will be xz square is equal to some arbitrary constant. So anything is okay. Another arbitrary constant, right? So here the initial conditions are, it is passing through 1 comma 1 comma 1. That means if you substitute here, so c value, or here b value, if you want to find it out, x is 1 and z is 1, then b is equal to 1. Similarly, in this case x is 1, y is 1, so c is also 1. Then the equation of these streamlines are xy square is equal to 1, this is one set, and another is xz square is equal to 1. So these two together will represent the streamlines equation. So these streamlines are in space. Got it? Understood? Note down one more. Yeah, so that y is equal to z is also one more set of streamlines. Yeah, that is true. But actually, here it's not one more set of. All the equations together will represent same set of streamlines. Got it or not? So for that, actually different relations were given, but all are interrelated to each other. So you may say this one and this one together, or so this one and this one, or this one and this one together. So any set you can represent, but essentially it will convey the same set of streamlines in space. Got it or not? The way you look at on the xy plane or yz plane or zx plane, how these are looking like, that's what is conveyed by those three equations. So three planes are there: xy plane, yz plane and zx plane. So on each plane it will give one equation. I hope now it is appropriate. Okay. Note down one more. Determine the streamlines. And the path of the particles. And the path of the particles u is equal to x by 1 plus t, v equal to y by 1 plus t, w is equal to z by 1 plus t. Can you solve this? Done? At least the first part is done. Streamlines. That should be straightforward. Yeah. So here dx by u is equal to dy by v is equal to dz by w. So out of all the three, this 1 by t is 1 plus t is common. You can cancel it out. Finally, what is left is dx by x is equal to dy by y is equal to dz by z. Or if you integrate it, then taking these two together, log x equal to log y or log cy, I straight away call the arbitrary constant. And then log x is equal to log cz or bz. Here x is equal to cy and x is equal to bz. So these are the streamlines equation, right? And then he asked us to find out the path of the particle. So when he asked to find the path of the particle, so that means this is as if like he asked the Lagrange's method, right? So Lagrange's method, actually he tries to trace the path of the particle starting from the initial condition. Now here u is given as x by 1 plus t, but u is nothing but, or the velocity vector is nothing but dr by dt is the velocity vector, or this is dx by dt into I plus dy by dt into j plus dz by dt into k. So this is the velocity, right? So this velocity is nothing but u is equal to dx by dt. So this is given as x by 1 plus t. Similarly, v is equal to y by 1 plus t and w is equal to z by 1 plus t. So dx by dt is equal to x by 1 plus t, or dx by x is equal to dt by 1 plus t. Similarly, dy by y is dy by dt is equal to y by 1 plus t. It implies dy by y is equal to dt by t, dt by 1 plus t. Similarly, dz by z is equal to dt by 1 plus t. Now if you integrate on either sides, then what you are going to get it is log x is equal to log 1 plus t. Log cx is equal to log 1 plus t, or this is, yeah, so cx is equal to 1 plus t. And then here ay is equal to 1 plus t, and here bz is equal to 1 plus t. This will give the path of the particle. Here this a, b, c are the arbitrary constants. Now this x is equal to 1 plus t by c, and y is equal to 1 plus c by b, and z is equal to 1 plus c by a. So all these things are nothing but the xyz coordinates of the particle at any instant of time. So indirectly what we are trying to express here, it is the path of the particle at any instant. Got it? So the xyz coordinates you can express it. X comma y comma z is nothing but, so 1 plus t by c, 1 plus t by b, 1 plus t by a. So these are the particle coordinates at any instant of time. So if you notice, all are the functions of time, but these are the xyz positions which are corresponding to it. Clear? Understood? No, you don't need to plot the graph. If you ask to plot the graph, then you can do that. Otherwise, you can leave it. So I hope you will be able to solve the questions related to streamlines, right? So suppose if these streamlines are asked to find out in the polar coordinate system, then you have to correspondingly adjust the equation. That is, so the dr by ur is equal to r d theta by u theta. Spherical coordinates r sin theta d phi divided by u phi. So these are the velocity components. In radial direction. This is the velocity component in the direction of theta. And this is the velocity direction in the direction of phi. So the procedure is same to find out the streamlines, irrespective of the coordinate system, whatever we selected. But correspondingly, this equation needs to be adjusted. If you notice, all are length components. Note down one problem related to this. Note it down. This is in spherical coordinates. Suppose this is cylindrical coordinates. This will become dz divided by uz. That's it. The rest of the thing is as it is. Determine the equation of the streamlines. Equation of the streamlines at the point in the incompressible fluid. At the point in an incompressible fluid, having spherical polar coordinates, having spherical polar coordinates r comma theta comma phi. The velocity components are the velocity components are 2r power minus theta, 2r power minus 3 cos theta, comma 2r power minus 3, 2 is not there, r power minus 3 sin theta, comma 0. So these are the coordinates. These are the velocity components. So this is ur, this is u theta, and this is u phi. Now can you solve on your own? Got it? Anybody got the answer? This is straightforward, right? See this. dr by the radial component of velocity 2r power minus 3 into cos theta is equal to r d theta divided by r power minus 3 into sin theta is equal to r sin phi d phi divided by 0. So this is the equation of the streamlines. Now, so if these are the equations of the streamlines, so by taking any of these two equations which is involving the last one, right? So r sin phi d phi equal to 0 or d phi equal to 0. If d phi equal to 0, then phi equal to constant is nothing but the equation of these streamlines at one plane. So phi equal to constant. That means that angle is constant. And by taking any of these two equations together, then this will be, so dr divided by 2 cos theta is equal to r d theta divided by sin theta. This is the equation, right? Then it will be dr by 2r is equal to cos theta d theta by sin theta. Now, if I take sin theta as t here, half log r is equal to sin theta, if you take it t, then derivative of sin theta is cos theta. So numerator, so this is dt by t, where t is equal to sin theta. Got it? So this is log t, so log of sin theta. Then if you take this 2 to the other side, then log r is equal to log plus log c here, log c sin square theta. So from that equation you can conclude that r is equal to c sin square theta and phi equal to constant will together represent the streamlines in the spherical coordinate system in space. Got it? Understood? Okay. So from tomorrow onwards, I wanted to change the timings to 6:30 in the morning because I think there are some power cuts here. So some lighting issue is coming. So we can have class from 6:30 to 8 from tomorrow onwards. I hope it should be fine. Okay, fine. So one important concept is continuity equation. So this continuity equation is based on the fundamental physics principle of law of conservation of mass. Law of conservation of mass, right? So mass can never be destroyed nor created, right? So based on this principle, this we are going to solve it. So the continuity by definition, right? If it has to be a continuous flow, then there has to be some law associated with it. That law is law of conservation of mass. So what it says is, suppose if there is a closed volume like this is a random closed volume. On this random closed volume, right, suppose if, let us say, the velocity of the fluid is going in this manner. So let us say this is flowing with a velocity of q. Then the normal vector at this particular point, let us say this is q direction, and let us say the normal direction, so this is n cap direction. So this is the normal to the surface, normal. That is normal to the surface. Now the effective velocity in the direction of the normal will be obviously equal to the effective velocity in the direction of normal to the surface. So that is n dot q. N dot q is the velocity in the normal direction. So this will be the effective velocity. I hope you are aware of this fact. That is, suppose if there is a pipe like this, on this pipe, let us say there is one slant. Yeah, so there is a slant kind of cut is there like this. Cut, I mean, here actually the water can flow. So the water is flowing like this. Now I have taken one more surface like this, exactly perpendicular to the flow. Then whatever the quantity of fluid that is traveling across this particular surface is exactly equal to the same quantity of fluid that is going across this particular surface, right? Correct or not? Because it is on the same tube. Obviously the same particles, whatever is traveled out of this surface, has to cross this surface as well. Got it? So, but here the slant surface is more. Surface area is more, but the surface area is less. But it is perpendicular. That is the only advantage it is having. Though it is less, but it is perpendicular to the flow. That's what is 100% effectively used here. But here, only partially it is going to be used. There is a component of the effective surface that is going to be used. That component is matters. Here the slant surface, though the area is more, but the effective surface will be less. So this will be taken care with the help of the dot product to the surface. So this is the surface and this is the velocity direction. If you want to find out the component, then you have to identify the dot product between these two. That's exactly what we have done here. Understood? Got it? So now actually, yeah. So this is n dot q. The effective volume of the fluid crossing the elemental surface area ds will be, so here actually the fluid is within this, right? And then let the density of the fluid, rho is the density, and then you have considered an elemental area here whose normal is n cap. So this is the elemental area ds. Now the volume of the fluid that is crossing with a velocity of q for an elemental area of ds and having a density of rho will be how much? Density is rho and the velocity of travel is q. and the area that it has to cross is ds. Can I guess how much it is? Obviously, the volume of the fluid that is going out will be ds into q, right? Correct or not? Yeah. So ds into q is the volume of the fluid that is going out, because the surface area or the cross sectional area and the fluid is crossing, right? So it has to be the volume of the fluid crossing the surface. This is equal to, so q dot n cap into ds. So this is the volume or the dv, right? Now here mass of the fluid crossing, dm is equal to rho into dv. So this is rho into q dot n cap into ds. So this is the mass of the fluid that is crossing out of this particular elemental surface area. Got it? Or if you integrate it, then it will be the total mass that is crossing over the entire closed surface area. Got it? So the total mass that is crossing will be crossing the surface area will be m is equal to, so per unit time, yeah, dm by dt. So this will be double integral over the surface S rho into q dot n cap into ds. Got it? So note down till this point. I'll continue it. Why twice integration? You shouldn't be asking this question. So we are talking about the surface. So surface will be two-dimensional. That's why actually it will be the total surface that you have to be considering here. So this will be a double integral, then only you will get the surface area. So this was covered elaborately when I dealt with calculus. Noted down? Okay. So now actually we have identified the volume of the fluid that is crossing the surface. The fundamental principle behind this continuity equation is the volume of the fluid entering the surface, not the leaving. Entering the surface is equal to the time rate of entering the surface per unit time is equal to the time rate of change of mass of the fluid within the closed volume or within the closed surface. So this is the base principle that we are going to use to find out the continuity equation. So this is most obvious. Suppose if the fluid is entering this particular surface, the same has to be accumulated by this. The time rate of change of volume of this particular space, right, or this particular mass, the time rate of change should be exactly equal to per second how much volume is entering inside, or how much mass that is entering inside. Got it or not? The time rate of change of mass within the surface is equal to the mass that is entering per second by the surface. Got it? So based on that principle, we will be identifying the continuity equation. So this itself is the continuity equation, but in mathematical format that we are going to do it now. So this is the mass of the fluid that is going out. Suppose if I ask you to find out the mass of the fluid that is coming inside, then it will be the negative of it. Got it or not? Because the velocity direction is taken as outward. But I am trying to find out the mass of the fluid that is entering, which is nothing but negative of this one. Got it? So the mass of the fluid entering per unit time will be minus double integral over the surface S rho into q dot n cap ds, and this will be equal to minus triple integral over the volume V rho into del dot q dV. I hope you understood that. You keep this rho also inside, so that actually you can even analyze changing density fluids also. Is this understood? What is the principle behind this equation? So this is what is the Gauss divergence theorem. So as per Gauss divergence theorem, whatever the fluid that is entering a closed surface is always equal to the mass accumulated within the surface, right? So this is the Gauss divergence theorem. So surface, over this particular surface, whatever is entering is nothing but the volume that is accumulated within. So this was stated by Gauss divergence theorem. That's why del dot rho q. As I told you earlier, del dot is nothing but the divergence is nothing but the accumulation capacity, or how effectively it is getting accumulated. That's what is del dot. So if del dot q is equal to 0, then we call that as solenoidal fields, right? Solenoidal fields means that is, incompressible fluids. Incompressible fluids. That means you cannot compress it anymore. I have explained yesterday. So that is based on del dot only we have decided that. So how much effectively it is compressed. The same thing should be equal to the volume that is entering. So from this is minus triple integral over the volume del dot rho q dV. So this is one side. Then the time rate of change of mass within the fluid. So here the density of the fluid is rho, and let us say if you take an elemental mass and then find out the volume, rho into dV is nothing but dm. So rho into dV is nothing but the mass, because the density into volume. So if you want to find the entire mass, then this will be the integration. Then m is equal to triple integral over the volume V rho dV. Here, if I have done single integral means this is not a single integral. This is a volume integral because this dV decides how many integrals that I need to write it here. Got it? So this is not a single integral. So this is this one, rho dV, because you are trying to do the integration over the entire volume. Volume is a three-dimensional space. So that's why it will be a triple integral. So rho dV, and then dm by dt. If you want to find out, dm by dt is nothing but the rate of change of mass within this particular surface. So that will be triple integral dou rho by dou t into dV over the volume V. Got it? So as per continuity equation, this mass, whatever dm by dt, whatever we have calculated earlier, this is the dm by dt. Whatever we have calculated, this will be triple integral over the volume V dou rho by dou t into dV is equal to minus of triple integral over the volume V del dot rho q dV. So this is the law of conservation of mass. Is this understood? This is the rate of accumulation of the fluid within this particular one. Is there an audio issue? I don't think. Others? Can you please confirm? Yeah. Anjali, can you please check at your end? Okay, anyway, so look at this. So triple integral over the volume V dou rho by dou t into dV. This is nothing but the mass of accumulation. Mass accumulation per unit time. Here, this is nothing but the mass that is entering the surface per unit time. Per unit time. Right? So here, the mass accumulated per unit time is nothing but the mass that is entering the surface per unit time. That is most obvious. By common sense we can make out. So this common sense is the continuity equation. So this is the continuity equation. Now this is the integral form. In short, you can write this continuity equation as, because both are triple integrals and both are volume integrals. So you can equate dou rho by dou t is equal to minus del dot rho q. I'll just write it here. Dou rho by dou t minus del dot rho q, and this is equal to 0. This is the shortest form of that continuity equation. Got it? Sorry, this is minus, right? So this is coming as plus. Yeah. So this is the fundamental principle of continuity equation. Note down this. Done? Okay. So this equation, whatever we have derived, right? So this is a master equation. So this is an equation of continuity for all kinds of fluids it is. That means homogeneous, non-homogeneous, time variant, time invariant, or steady, all kinds of fluids actually. This is the master equation. Now this is, if we expand further, dou rho by dou t plus del dot rho q equal to 0. Or this is dou rho by dou t plus rho into del dot q plus q dot del rho. Q dot del rho. Now this is equal to 0. If I write these two together, dou rho by dou t plus q dot del rho plus rho into del dot q equal to 0. Or this is dou by dou t plus q dot del of rho plus rho into del dot q equal to 0. So here, if you notice, this is nothing but the substantial derivative or the material derivative. So this is the material derivative. So d by dt of rho plus rho times of del dot q equal to 0. Now, if rho is a constant or if it is a steady flow, then dou rho by dou t will be 0. Then if rho is constant with respect to time, and this is also called as steady flow. For a steady flow, there won't be a change with respect to time. So then d rho by dt equal to 0. Then the equation is rho into del dot q equal to 0, or in short, del dot q is equal to 0 for an incompressible fluid. So for an incompressible fluid, it should be del dot q is equal to 0. Got it? Steady and incompressible. Clear? So this is how actually we will be analyzing, but the master equation is this one. So if you remember this equation, then you will be able to derive the continuity equation for any kind of fluid it is, whether it may be a steady flow or unsteady flow, compressible, incompressible, all kinds of fluids. This is the base relation. But for an incompressible fluid, obviously, so here actually, if rho is constant and incompressible, then del dot q obviously equal to 0. Got it? Any questions on this? Okay, so this is the master equation, which is nothing but the continuity equation. So the complexity that is getting involved in the continuity equation is not in understanding this derivation, but rather when we are solving the problems, right? So the different kinds of coordinate systems that are going to come into picture. So that's where the difficulty lies. Yeah. So in the spherical coordinate system, Cartesian coordinate system, cylindrical coordinate system, when we go with the details, then the complexity will come for this continuity equation. Got it? Okay, so I think so with this I would like to stop the class for today. In the next class, let us see if there are certain problems we can solve on this, and based on that we will proceed further. Yeah, so till then, thank you. Yeah, good morning.